End of topic test on magnetism and electromagnetism for the separate physics. So this question is about magnets. Which statements apply to permanent magnets, which apply to electromagnets, and which apply to both? Tick the correct boxes. So needs an electric current to work, that's for electromagnets. Have a constant magnetic field, that's permanent magnet, can be turned on or off, that's per electromagnet. Have north pole and south pole, that's both. Often contains a coil of wire, that's for electromagnets. What is an induced magnet? That would be a temporary magnet made by touching a piece of steel with another magnet. Next question. Describe how to find the direction of the magnetic field around a permanent magnet using a small compass. Again, I insist draw a diagram which actually helps you with the answer. So, and you can change the orientation to help you out. Place magnet on paper, trace around it, place compass next to one end, mark direction of compass, move compass further to tail, which is the south of needle, now points to marked point, and mark again. Repeat till you come to the end of the paper or to the poles. Join the dots. Direction of arrow is of compass is equal to the direction of the magnetic field. Next question. A student was investigating the effect of the size of current on the strength of an electromagnet. Figure 1 shows the equipment she used. So that's the figure. As you can see, if it's not switched on, this iron disc will actually weigh, let's say it's about 1 Newton, right? That's the starting force. So you need to, if you're actually doing this, and if you're taking measurements, you will have to take away 1 Newton from the force that you're actually measuring, because when you switch it on, right, a magnetic field is produced in the coil, right, that will produce or create a electromagnet because of the iron core, and that iron core will attract this weight down. Now the way it actually attracts depends on the strength of the magnetic field. The strength of the magnetic field depends on the current. The question is asking, describe how the student could carry out an investigation to find the relationship between the current in the coil and the force on the iron disc. So start at 0 amps, then increase current to in intervals of 1 amp up to 5 amps. For each value of the current, record the force on the Newton meter, right? Repeat 3 more times, then draw a graph to show a pattern, right? I haven't mentioned about taking away the 1 Newton force, but what they want is actually describe how you could carry out the investigation. So to find the relationship, you need to focus on drawing the graph, right? Even if you did include it, the error is always going to be the same. So if you did draw the graph, the current, which is I, and the force is what you're increasing the current, right? So it won't start at 0. It'll start somewhere there like that. If it's a straight line or a curve, it'll just start at 1 Newton there, right? The student makes 2 electromagnets, one with 100 turns in the wire in the coil and one with 200 turns. She carried out the investigation with each of the coils and plotted graph 1. So you have the 200 coil and the 100 coil turns. The student wanted to find the ratio of the force from the 2 different coils at each current. So you've got the current for up to 5 amps and the force in each of the coils. So if I were, for example, at 2 amps, you're literally finding the values in both of those points. So complete the last row. So at 5 amps, so when it's at 5 amps, you would draw a line. Again, I see very few people actually using a ruler, right? At 5 amps, the current is, for the 100 turn coil, is 0.44, and for the 200 it's 2.18, and the ratio, if you divide 2.18 by 0.44, you should get 4.954. Now because they've already given that in 3 significant figures, you can give that as 3 significant factors. 1:4.95. Next question. The student wrote the following conclusion: the relationship between the current and the ratio of the force from the two coils is directly proportional. Now, that's not actually correct, because if it was directly proportional, both these lines should actually be straight lines. It's actually curved, right? So they're increasing, right? They have a positive correlation, but they're not directly proportional. So was the student correct? No. As current doubles from 1 amp to 2 amps, right? So if I'm using the table to help me out as well. So as the current doubles from 1 amp to 2 amps, the ratio stays actually the same. When you go from 2 to 4, the ratio is still not actually doubling, right? It's not going from 3.5 to 7. It's only increasing slightly. So if 1 amp to 2 amp ratio does not double, it stays the same. As current doubles from 2 to 4 amps, the ratio, right, does not double again, right? Question 3. The left-hand rule can be used to identify the direction of the force acting on a current-carrying conductor in a magnetic field. Label, right? Again, these are easy marks where you should be getting. The thumb is the force. Remember, F, B, and I. So, force, field for magnetic flux density, and I is for current. Figure 3 shows a wire held between the poles of the U-shaped magnet on the top band balance. The magnet was placed on the top band balance before the current was switched on. The balance was 0. After the current was switched on, the balance read 161 grams. The arrow shows the direction of the current in the circuit. Which direction was the force on the balance? So, the force is acting down on the balance. That's why you're recording a weight being recorded on the balance. So, it acts down on the balance. Next question. Due to Newton's third law of motion, the force on the wire is in the opposite direction to the force in the balance. Which direction was the magnetic field? So, Newton's third law states, right, if there's a force acting down, which is the force from the wire, right, there's a force acting upwards. Now, the question here is, which direction was the magnetic field, right, from the front of the balance to the back of the balance? How did I work this out? Going back to this diagram, right? Remember, the current is actually, right, so that's my middle finger, right? So that's the current, right? Force, field, current, right? So there's a force acting up. My thumb is pointing up, and the direction of the magnetic field is from the front to the end. Hence, I put an arrow with the north and the south, like that. Explain what would happen to the reading on the balance if the current in the wire was increased. The force value would increase since the magnetic flux density on the wire increases with the current. You have to link the magnetic flux density to the force for those 2 marks. Question number 4. One simple design of the electric motor is shown in the figure. It has a coil which splits between the poles of two magnets. Add an arrow to figure 4 showing the direction of the current in the wire from the battery. So again, using Fleming's left-hand rule, magnetic field is actually moving in this direction, right? Force, field, current. So, right, looking at this, that's my current direction. The magnetic field is actually in this, and my thumb is automatically pointing up. So the current is actually moving in this direction. So that's anti-clockwise direction. The motor is part of an electric drill. It needs to be able to change direction and speed. Describe the direction and speed of the drill. how the direction and speed of the drill could be varied without changing the way the motor is constructed. You reverse the current or increase the current to increase the speed. So to reverse the direction, you reverse the current. 4.3. State two other ways that the construction of the motor could be changed to increase in speed, increase the number of coils in the wire, or increase the strength of the magnet. 4.4. A student builds a model motor. The magnetic field between the poles is 3 times 10 to the power minus 2 Tesla. The length of one side of the coil is between the poles is 2 centimeters. Remember, you need to change it to meters. Hence, it's 0.02 meters. The current is 0.5. Calculate the force in the coil. F equals BIL means that you multiply all those values and you will get 6 times 10 to the power minus 4 newtons. Question number 5. Figure 5 shows a part of the national grid. So you have the power station, transformer C, then the overhead cables. These are the pylons, and then transformer D. Transformer C and D are different types. Explain why 2 different types of transformers are needed in the national grid. For 3 marks, the main mark is actually for transformer C and 1 mark for this. So C is a step-up transformer. To identify if it's a step-up or a step-down, it's the 1 mark. So that's a step-up transformer, that's a step-down transformer. Why do you need this? You need a step-up transformer here to reduce the current in the power lines. If the current is high, then there's going to be more resistance and you lose a lot of heat. So to reduce the current in the power lines, so less energy is lost as heat, which increases the efficiency. D is a step-down transformer to decrease the potential difference, right? So here usually you have about, let's say, about 25,000 volts, and in the power lines it's usually about 125,000 kilovolts, and then you need about 240 volts, right? So as you can see, it's actually increased by a massive amount, and then it has to be reduced. D is a step-down transformer to decrease the potential difference, and it actually increases the current as well, right? To make it safer for users, right? For it to be used. So you can't power electrical appliances with low current. So you can either say it's to make it safer because the voltage is too high, or you can say it is done to increase the current. Next question. The cables used in the national grid can either be suspended from pylons or run overhead or buried underground. When an electric current flows through a transmission cable, a magnetic field is produced. Figure 6 shows how the strength of the magnetic field varies with distance from both overhead and underground transmission cables that carry the same current. For the same current, an overhead cable, the strength of the magnetic field starts at 6, and by the time it's 50 meters away, it drops to 0. If it's underground, it actually starts at 10, but within about 5 meters, it literally drops to about 3 arbitrary units, and by about 30 meters, it's gone down to 0. A politician sees figure 6 and says underground cables are safer as they have a lower strength of magnetic field. Evaluate his claim. He is correct, right? He is correct since the magnetic field from underground cable drops off in a shorter distance. But there is no link to safety in the graph. He's talking about it is safe. How would he know? Just basically based on this, right? There's no medical evidence for this. That's why the second mark is actually saying, but there is no link to the graph. That's the evaluation. 5.3. The slope of the graph shows the rate of change of magnetic field strength with distance. Calculate the slope of the graph from the overhead cable between 0 and 20 meters. So looking at the graph here, 0 and 20 meters for the overhead cable, and if you draw a line, it's about 5.46. The difference is 0.6, right? So it should actually be minus, right? 0.6 divided by 20, and that gives you an answer of minus 0.03 arbitrary units. Question number 6. figure 7 shows a transformer, and you have the iron core with the primary coil and the secondary coil. Explain why it is not possible to use a transformer with a battery. A transformer requires an AC current to produce an alternating magnetic field. A battery produces a direct current. Remember how a transformer works. When you pass a current through the primary coil, it produces a magnetic field there. That magnetic field causes the iron core to be magnetized, and the magnetic field of the entire iron core now changes along according to the frequency of the current in the primary coil. Because the secondary coil is now in a changing magnetic field, a potential difference is induced in the secondary coil. Describe the construction of a step-up transformer. Right? You can be asked about the construction of the transformer if you're in separate science. If you're in combined, then you don't have to be bothered. It contains a central iron core with 2 coils of insulated wire around it. Its primary coil has less number of turns than its secondary coil. Remember, it's a step-up transformer. Question number 4.3. State 2 other ways that the construction... No, I'm going back. Right. There you go. 6.3. A transformer has 2600 turns in the primary coil. So, number of turns in the primary coil is 2800. And 700 turns in the secondary coil, that's NS. The potential difference across the secondary coil is 12 volts, that's Vs. Calculate the potential difference across the primary coil. NP over NS, remember it's a ratio, equals Vp over Vs, which 2800 divided by 700 equals Vp divided by 12, and gives you a final voltage of 48 volts. Now, the last question. Figure X shows the parts of a device used to measure earthquake called a geophone. Now, before I move on to this, you need to link this question to the basic idea of what happens. Right? I did this in the lesson. If you have a coil of wire and you attach it to an ammeter, right? So it's just simply a solenoid. And if you have a magnet north and south, if you move that magnet either towards or further away, right, from the coil, there's magnetic field that is actually coming from this bar magnet. As the magnetic field cuts across this coil, a potential difference is induced and you're going to get a current. Now, if you move it in, the current is going to be in one direction. If you move it out, the current is going to be in the opposite direction. So moving it back and forth will produce a current that is going changing direction both sides. If you move it fast, because the magnetic field is actually cutting the coils fast, you're going to produce a bigger current. It's the same principle that is being applied here. Now, the coil is actually just given as a really thin, but it's actually still a coil. So, imagine this same diagram like this, where you have the magnet suspended when it's going to be moving up and down. So, looking at this, these two springs will actually allow the magnet to move vertically up and down, right? Freely with very little resistance. When it moves, that's going to interact with the coil. The magnetic field is going to interact with this and it will produce a current which is going to come off from the terminals, and because it's connected to an ammeter, you can actually measure the current, right? So now the entire thing is actually attached firmly to the ground. The spike attaches the geophone firmly to the ground. An ammeter is attached to the terminal. When an earthquake occurs, the case and the coil move up and down due to the Earth's movement. So if the Earth is actually moving up and down, so you can get earthquakes which is actually moving up and down, which causes buildings to literally jump up and down, and those are as a result of transverse waves. If the building is actually shaking, this won't work. So you could actually have a geophone which is similar to this, right? Because the magnet is heavy, it does not move during an earthquake, right? So this is something to do with something called inertia, right? This magnet, because it's heavy, it doesn't actually move easily, right? So when the entire thing is shaken, right, the magnet refuses to move because of inertia, right? And the coil is moving just in the magnetic field. Now, as it moves, the more the earth shakes, the more the coil moves, the more current is actually generated, right? That links to how it actually works. So that's what the question is asking. So explain how the readings on the ammeter would change when there is no earthquake. If there is no earthquake, no magnet movement, so no current in the coil or no potential difference is induced. If it's a small earthquake or a large earthquake, the coil moves during an earthquake relative to the magnet. So comparing to the magnet, the coil actually moves, not the magnet. The magnetic field cuts through the coils, so a current is induced in the coil. The current changes direction each time the movement of the earth changes. And it will be the same frequency to produce the AC current. A large earthquake would produce a larger amplitude, producing a larger current. That's the 6 marks. That brings to the end of the test paper. The last thing that I want you to do is actually to go through this feedback form with the instructions. Now, I want additional feedback. This is for you for self-reflection. Read through this information and then fill this bit. Because you're self-assessing, I will not be able to give you a teacher review, but in order for me to do this, I will need information from you in terms of the number of marks. I will explain that in the classroom.